We're fortunate to have such an expert on cold fusion here with us today. Professor Hagelstein got his BS, MS, and PhD at MIT in electrical engineering and computer science. And he spent about a 4-year period working at Lawrence Livermore National Labs on X-ray lasers and soft UV lasers, where he won a number of awards. Importantly for this talk, he's been investigating various aspects of cold fusion for 30 years and has written over 50 papers on the topic, often with other key contributors in the field. He chaired the 10th International Conference on Cold Fusion in Cambridge, Massachusetts, I think 2003. And he teaches a course in independent activity period on cold fusion at MIT. It's now my pleasure to introduce Professor Peter Hagelstein.
Okay, can you hear me?
Yeah.
So, that's not my talk.
Oh, no.
Is there?
Oh, no.
It's probably down here. Try this PDF. Oh, yeah, try the PDF one.
Heart failure. Oh, no.
Here.
Kill that one.
Yeah, let's kill that one.
That's okay.
Because that's not going to be used at all.
Okay. Cold fusion. In my view, it's real. Is it ready? I'm going to start out with some early history. Okay, so I know that I speak softly. If you can't hear me, go like this, and I'll try to speak louder. So back in 1989, Fleischmann and Pons stepped up in front of the microphones and announced cold fusion. And a paper was written. Paper didn't contain many technical details. I will fill in some of the...
Peter, you're going to have to move the mics down.
Okay, so the Fleischmann-Pons experiment was electrolysis of palladium cathode in heavy water. Deuterium confused with a deuteron confused with another deuteron. Typically it will make proton, tritium, neutron, helium-3 in equal measure, roughly 50-50. In order to get that to work, people make very large machines to get the deuterium to move fast enough to overcome the Coulomb barrier. The claim, well, there are many claims. The one I'm going to be most interested in is the claim of large excess heat. No commensurate chemical product. Fleischmann conjectured that the effect was due to a nuclear effect, a new nuclear effect, with no commensurate nuclear radiation. It would not correspond to normal DD fusion nor to nuclear energy being made by any other method which people were familiar with. The initial problem for scientists, I initially had skeptics, but then I thought about it. Scientists, generally, no appropriate technical description was given in March 23rd, 1989, or during the weeks afterwards. That's on the experimental end of things. On the theoretical end of things, whatever effect was going on was an unknown effect. What was under discussion was something new, something different. So, what to do? Well, on theory, what was done, what might have been done, might have been to consider what process might work that way. What was done instead was to focus on two deuterons fusing in molecular deuterium. Many people focused on this and did the calculation. Coulomb barrier keeps the deuteron nuclei apart. They can tunnel. The fusion rate for molecules is very slow. The argument is that since things are so slow for the molecule, you wouldn't expect to see anything in palladium deuteride. On the experiment end, again, in the absence of having technical documentation of Fleisch and Pons experiment, well, what do? Many experimentalists went ahead and started loading palladium cathodes with deuterium. MIT carried out a very famous experiment, and in their publication they showed data like this. Basically, they tried it, it didn't work. Many other groups tried it, also came to the conclusion that it didn't work. This was circulated widely around MIT. It's a wake for a cold fusion. The date of the wake I draw your attention to is Monday, June 26th. Announcement March 23rd, wake June 26th. This didn't take very long to sort out what the story was. There's a electrochemist, Dieter Britz, who put together a bibliography. Britz is no friend of cold fusion, and so he used as a filter that he wanted the papers to be published in a refereed mainstream non-cold fusion journal, and conference proceedings papers weren't allowed. And from this particular filtered version of publications, there's 217 papers, all with negative experimental results. You don't come back from something like that. The outcome was probably inevitable. The ERAB committee came up with a negative conclusion. John Hazenga, who is co-chair of the ERAB committee, wrote his book, Scientific Fiasco of the Century, Frank Close's book, Gary Taub's book. There are other books, and that's how it ended. Thank you for your attention. Now, perhaps we ought to think a little bit about the experiment. So I have a few slides which attempt to begin to get us oriented as to what the Fleisch and Pons experiment is as an experiment. You can imagine the electrolyte containing D2O. So I've got a cartoon for my D2O molecules. The palladium is here. The lattice is such that there's holes in the middle where you have the possibility of having hydrogen or deuterium go. If you load the cathode, then Volmer reaction brings deuterium, puts it on the surface, it diffuses in, and you get interstitial deuterium. So in essence, the Fleisch and Pons experiment does that. It takes deuterium that's in the electrolyte, brings it to the surface, gets it inside the palladium cathode. This is a version of the phase diagram. Phase diagrams we use to torture students still at MIT. I'm sure you remember how it works. The basic idea is that this atmosphere is pressure, this is loading, this is, in this case, palladium hydride, how much hydrogen you have for palladium. And there's a miscibility gap here, and basically it means operationally that near room temperature you can load pretty easily with much less than an atmosphere. It's easy to load up to 0.6. If you want to load up to 0.7, you got to put your back into it. If you want to load up higher to 0.8, 0.9, you basically have to be heroic. If you want to load up close to 1, that's you got to get up to about a gigapascal, and that's serious pressure. The equivalent pressure is a way to keep track of the associated thermodynamics in the electrochemical system. Good electrochemistry can give you equivalent pressures that high. If I focus on the high end of things, here's what it looks like for hydrogen in palladium. This is from a model that I constructed from data. At the low end of things, the experiment matches the data beautifully. For palladium hydride, there's data at high loading, and that's good. For palladium deuteride, there's some data as well, and match that. But basically, you see 0.7 loading for palladium deuteride, 10 atmospheres or so. 0.8, you're 600 or so. 0.9, you're several thousand. To get near 1, you're over a gigapascal. There's 10,000 atmospheres equivalent. The takeaway message here is that if you want to get high loading, you have to be prepared to do some serious electrochemistry. And my friend Mike McCouvery, he's an electrochemist. He's still my friend, being an electrochemist. He used to think of the cathode like a balloon. You load it, you bring deuterium, put it in. If it leaks out, so Volmer reaction brings it in, Tafel reaction, it goes out. If you can maximize the in, minimize the out, you can get high loading. And his trick was to put aluminum or silicon on the surface so it blocks sites. So you don't go in as much, but you don't go out as much squared. And that helps. The diffusivity, if you want the deuterium to go in, well, it's got to move around. And the diffusion coefficient's important. At low loading, the diffusion coefficient's high. At high loading, the diffusion coefficient's high. In the miscibility gap, it's low. That gives you a headache. And the basic headache is that where the diffusivity is low, you get these discontinuities. And that's important because at high loading, the lattice spacing is 10% larger than at low loading. And if you're pushing high loading through low loading and you're changing lattice spacing, you can imagine the lattice isn't going to be so happy with that. It kind of like gets chewed up pretty bad. So to avoid damage, you basically would like to load slowly to avoid damage. In the Fleisch-Pons experiment, loading slowly might mean a month and a half worth of loading time. Fleisch-Pons made use of isoparabolic calorimetry. Basic idea is you measure a temperature somewhere inside, you have a reference constant temperature outside, and then the difference temperature is due to the heat flowing through, so you can estimate your power from the temperature difference. If there's dynamics, you can solve a differential equation. Again, fond memories from time at MIT or other places. Electrochemists and physical chemists have used isoparabolic chemistry for a very large number of years. It works. Fleischmann was interested in the integral version of it. The basic idea is if you've got a solution to your equation you can match against the data, you can get a more accurate fit for your calibration constant, and you can do better calorimetry. This is significant because in the criticism that was leveled against Fleisch-Pons, one of the big criticisms was that Fleischmann did it this way, of course with a much more complicated model than what I'm presenting here, whereas the other electrochemists did it the differential way. Reproducibility was an issue in 1989, as today. McCouvery argued that back in 1989, around the time of the announcement, Fleisch-Pons only got positive results once every 5 to 10 cathodes. And that's significant because if you're testing it at MIT, there was one cathode tested with heavy water. So just an issue. And MIT wasn't the only one to test a small number of cathodes. Back in the ERAB report, actually back in Huizenga's book, Huizenga explained helpfully to people about how cold fusion works. Cold fusion, according to Huizenga, is a 10% effect, which is very hard to measure given the big signal-to-noise ratio problem. So there's lots of noise, really tiny signal, and so as a result, it's easy to understand how Fleischmann-Pons could be misled. In their 1990 paper, Fleischmann presented temperature data for run, temperature down here, excess heat burst, the temperature went up, and then it came back down at the end of the heat burst. I'm wondering what Heisenk was thinking about, and others have been thinking about when they've come by with very strong criticism of signal-to-noise ratio. Electrochemists can measure 20 degrees C temperature changes. The excess power, again, Fleischmann or Heisenk and other critics said that the power gain 10%. Fleischmann and Pond's publication, same 1990 publication, the power gain was estimated to be a factor of 20. In terms of the energy gain, according to Heisenk, the energy gain is 2 or 3%, and there was no calorimetry around that was being used for cold fusion experiments that could determine energy unambiguously at the 2 or 3% level over a long time of an experiment. In Fleischmann-Pond's experiment, their 1990, the energy gain was about a little bit more than a factor 2. In this experiment, 630 kilojoules were reported having been produced. 630 kilojoules over 60 hours, 2.9 watts. If you took an equivalent volume, 0.157 cc, as that was the volume of the palladium cathode, but if you replace the palladium cathode with TNT and detonated it, you get roughly 1.2 joules, a little bit less than the 630 joules. So the amount of energy produced, the claim is a very large amount of energy being produced. And because of the very large amount of energy being produced, Fleischmann was driven towards a conclusion that he was looking at a nuclear energy source, especially in the absence of chemical energy. Okay, let me catch my breath. When you say that you've reproduced the Fleischmann-Pons experiment, the question is, what experiment did you do? Because in the early days, there was no technical description of Fleischmann-Pons experiment. At SRI, they worked on a variant of the Fleischmann-Pons experiment. And what made their variant interesting is this graph. This is the resistance ratio associated with palladium hydride and palladium deuteride. The basic idea is that if you go way over here, you start at resistance ratio of 1 at no loading. As you add hydrogen or deuterium, the resistance increases due to disorder. It peaks around 0.6 or 0.7 or so, and then it starts going back down. So if you monitor the resistance ratio, you can figure out your loading. Hello? Hello? Okay. So if you've got your loading, then you can compare it and correlate it with the experiment. Now, McCoubrey's intuition was that people have studied palladium hydride and deuteride at low loading for decades, and from his perspective, no significant anomalies. So if there was going to be something interesting, it had to be at high loading. So the question is could you measure your loading, and if you got some excess heat, correlate it with your loading? A result obtained early on and published in 1994 looks like this. The loading is 0.85 here, 0.87, 0.89. This is 1 watt around here for that experiment. So Fleischmann, or McCoubrey, and others doing similar experiments concluded at the time that having high loading was either good for seeing excess heat or a prerequisite. In any event, there was a correlation. A protocol used at SRI early on looked like this. Not every cathode was a hero. So you start out with loading cells where your cathodes in here, recombiners up here, and you run lots of them, and you measure the loading in your different cathodes. When a cathode gets to a high loading, you promote it to your expensive flow calorimeter, and you do good calorimetry with it. And meanwhile, the ones that didn't load, well, we won't talk about what happened to the underperforming, but they had to be let go. Flow calorimetry. SRI used flow calorimetry, which was very expensive. Took a lot of work. The issue was in Fleischmann-Pons isoparabolic calorimetry, the way it was done, the criticism was leveled was a lot. Calibration constant might be an error. The electrolyte would boil off, and not boil off, it'd be turned into deuterium gas and oxygen, so it would go away. So you'd have to keep refilling your cell. And then if you calibrated it with a resistor, as was often done, the origin of the heat might be different than when you do a live run. I listened to some of the criticisms at the time, and I was worried whether anybody could measure anything to within 10% by the time all the criticisms had been leveled. The argument for the flow calorimetry is that you send in water at one temperature, it collects the energy, you don't let the energy go out other pathways, comes out at a different temperature, you measure the flow rate, you measure the temperature difference, and both of those things are much easier to do than keeping things going on the fly in a cell that's got electrolysis going on. At SRI, they were able to collect up to 99% of the heat. Recombination was another big issue, that in an electrochemical experiment, you make oxygen at the cathode. I have to read my figures more carefully when I download them from the internet. The anode, either the deuterium goes into the palladium or it bubbles out. There's a possibility of it recombining. In Fleischmann-Pons experiment, people argued, your excess heat effect is completely due to recombination. You aren't including it. Now, in their experiment, that could account for about 30%. It's like 1.5 volts over 4.5 volts or something. There's limits to how much effect it can account for. But in flow calorimetry, all the gases recombined. There's a closed cell, and so there's no issue with recombination, which is one of the reasons why SRI pursued it. So in one of their early experiments, the palladium deuteride cell gives excess heat. The one done in light water appears either to give much less excess heat or no excess heat. So in a sense, the light water experiment was used as a control. We'll return to that later on in the talk. As a function of current density, things look like this. At low current density, no excess heat. Above a threshold, the excess heat seems to be linear in current density. And these observations were repeated in other labs with similar results. As a function of loading, we showed data earlier. It's another experiment, loading 0.9, 0.95. So you recall, you have to load heroically to get very high loadings, but the excess heat appears to come at the highest loading in these early experiments. SRI noticed that excess heat was seen in cathodes that reached a very high maximum loading. So when the excess heat comes, the loading might actually be a little bit less. But if sometime during the loading history, a very high loading was observed, then the likelihood that the cathode would show excess heat would be very high. So big number here, smaller numbers here, because it's very hard to get cathodes to load this high, so there's not so many examples of them. The MIT loading was determined to be around 0.75, 0.78, no excess heat. The Caltech loading, 0.78, 0.8, 0.77, 0.8, no excess heat. So although loading is not the only thing that you need to do to see excess heat, it's one measure that you can use to figure out whether you're likely to see excess heat or not, again, at least in the early experiments. Okay, so we saw there were negative results. We've seen as positive results. I visited a physics professor in the early years at MIT, and he said, well, what you need to do is you need to read every paper with a negative result and explain to me what they did wrong, why they didn't get excess heat. Okay, so let's start with this. The thought is, back in 1989, in the early days after the announcement, people argued, well, if you've got fusion, you're going to make neutrons. you can measure neutrons one by one. So with a good neutron detector near a cell, you're going to be able to detect whether you've produced fusion energy more sensitively by 10 orders of magnitude than you can do with a calorimeter. So as a result, most of the early experiments were done with radiation detection rather than with calorimetry. Now, much later, we got some experience with experiments producing excess heat. And some of these experiments were done with neutron detectors next to them. And at least according to my analysis of the data and the experiments, there's no correlation between neutron emission and excess heat. And if there is a correlation, the upper limit for the correlation is about 1 neutron per 100 joules of excess energy produced. So what this means is that using a neutron detector is not a good way to see whether your Fleisch-Pons cell is producing excess heat. So if we go back to the gigantic number of negative experimental results and say, let's filter out the ones where they didn't measure a temperature. Let's set our bar really high. We want a temperature to have been measured in the experiment. We want the cathode to be palladium. We want it done in heavy water. Okay, we get 39 papers left. Now, 39 papers is still more than enough to rule out there being an excess heat effect. The second issue is that, as we've remarked, there were an absence of technical details about the Fleisch-Pons experiment in 1989. So one might ask, what were you testing? You can read in some of the papers where they argue, we're not sure of what we're supposed to be testing here. Some experimentalists are explicit about this. So we know from the SRI work and from other work that loading for these early generation experiments are important. So as a measure of seeing whether the researchers were paying attention to what was going on in the field and the positive results, we'll look at the negative papers to see how many mention the word loading somewhere in the paper. Again, I apologize for setting the bar so high. So we start with 39 negative papers, and we've got 22. Pretty good number. Now, mentioning loading is good. Question is how high of a loading? So suppose we set 0.83 loading as sort of being a minimum. Well, 7 of them got to loading of 0.83. 3 of them got all the way up to 0.9. The best of these was this one. This one was done by Green and Quickenden, who had been talking to McCoubrey about this and knew that loading was important, made an effort to get high loading. Now, high loading is one issue. McCoubrey used to goose the current to kick on excess heat. Green and Quickenden maintained the current absolutely stationary. At SRI, when they maintain the current absolutely stationary, no excess heat. Green and Quickenden was also a little bit low end of the loading that you'd need to have any luck. And there are other issues as well. Let's compare. Again, Green and Fritz is no friend of cold fusion, and we'll use his filter, which filters out all the conference proceedings where most of the positive excess heat results were published. And in his bibliography, there's more positive papers with palladium, heavy water, and temperature measurement than negative papers. Now, having said all this, Ed Storms recently is making a big issue that high loading's not a critical issue. And what he presented data here, he took the blue points here are excess heat for a cathode with bulk loading at the time the measurement was made of 0.80. And that's a bulk loading number. The surface loading we expect to be higher. It was working. He let some of the deuterium out, got the bulk loading down to 0.48. You can get these pink dots. And so once it works, if you've got less loading, it can apparently still work. These dots down here, when there's no deuterium left, it doesn't work anymore. So having a high loading in the early experiments appears to be a requirement. The issue here is once something's already working, you don't need to maintain the super high loading to keep it going. And we'll talk about some of the reasons why that might be true. Okay, let me come back to theory. And for theory, there are many theories that have been put forth. One of my friends who's a very good theorist is here. Another good theorist is here as well. I'm going to talk about the ideas I've pursued with apologies to my fellow theorists. As a tutorial, there's two kind of dynamics in quantum mechanics. There may be more than that. There's incoherent decay, where one state decays to many. This is called incoherent. So incoherent decay is what people doing DD fusion with accelerators do. The normal nuclear reaction is an incoherent reaction. Coherent process is the kind of thing that people in quantum optics do, where if you go in and get an MRI done, it's coherent. So the idea is you go from one state to another state to another state. That's an example, and there's many other examples. So D2 fusion is incoherent. A simple-minded picture, two deuterons, they tunnel together, they're close together. When they're close together, they interact on the order of 10 to the minus 21 seconds, which is faster than you can snap your fingers. And you get 3 in 1 combinations leaving. And during that time, which is faster than you can snap your fingers, it's really hard for this nuclear system to talk to the rest of the world. So not only are you unlikely to have any impact on this state from the rest of the world, but it's unlikely you're going to change the final product distributions as well. Okay, so in the early days, they looked at the D2 fusion rate, and they pointed out and said, molecular D2 doesn't fuse. That rules out D2 fusion with palladium deuteride. I'm scratching my head thinking about this. And I'm thinking, okay, I know from this kind of model, the D2 fusion isn't going to happen in palladium deuteride, at least incoherent D2 fusion. And I know from Fleisch-Pons experiments that they don't get the neutrons that correspond to the reactions that would be needed to make the heat. So in some weird kind of way, we actually have agreement. Theory says incoherent D2 fusion is not going to work. Experiment says incoherent D2 fusion is going to work. So they're consistent. And in fact, I'm wondering why in the world is there so much attention paid on the D2 incoherent fusion mechanism in the first place? Because Fleisch-Pons said at the outset they didn't get commensurate amount of nuclear radiation from it. Heisenka recognized this and he said, okay, let's make the argument stronger. And he demanded that if we were going to do theory for Fleisch-Pons experiment, we had to work with an incoherent theory, that we had to get the tunneling rate through the Coulomb barrier increased, which is impossible as far as I'm concerned. You have to suppress the normal fusion pathways to make helium-4 plus gamma, which is just impossible. And you've got to eat the gamma, which is impossible. And I'm scratching my head thinking about that. I'm thinking, this doesn't sound to me like a particularly promising approach to explain cold fusion. And if you're trying to limit it and rule things out, why not my version of a stronger thing? Based on the experimental results, you can rule out all candidate incoherent reactions which make energy with based alone on the absence of the observed absence of commensurate nuclear radiation. So I'm looking at this and scratching my head, and again, this is not particularly helpful if you're trying to make progress figuring out what in the world's going on in the lab. Let me scratch my head and think a little bit about the coherent reactions. And I'm going to start with what I'll call a mathematical one. When a physicist describes a process which sort of is mathematically possible but is so far away from the realm of real physics, you call it a mathematical example. You don't call it a physics example. So this is a mathematical example. So the idea is you've got so many D2 and you've got so many phonons in this case, because I've got to have some place to put my energy. Maybe I have one less here, and then I've got one more helium-4, and I got more phonons, and so forth. So I can get some states going back and forth. And for this kind of coherent process to work, I have to cache in the nuclear energy for a very large number of oscillator quanta, or in this case, phonons. Anyway, this is a mathematical example. The reason it's a mathematical example is that if we view this as a candidate physical theory, it doesn't work very well. It's off by so many orders of magnitude that you feel sad for it. Anyway, conceptually simple, if something like this could work, it would do the job. It would solve the problem of missing nuclear radiation. It turns out accidentally it solves the Coulomb barrier problem. I wasn't trying to solve the Coulomb barrier, but the rate is linear in the matrix element, and the matrix element has one tunneling factor, whereas incoherent rates go like the square of the matrix element, which has the square of the tunneling factor. So this approach gets you 40 orders of magnitude out of the box. Of course, you got these minor headaches. You need to split up the big quanta into 500 million smaller quanta. When I was first looking at that, I shook my head. I said, no, this isn't going to work. And then on the other hand, I thought, well, there's nothing else that's going to work, so let me keep plugging away at it and see what I can do with it. The matrix element's too small. How do you couple the nuclear degrees of freedom vibrations? And there's a model for this, and you can even use the model, and you can show by brute force calculation that it just doesn't work. Oh well. Okay, another try. I tend not to give up. Second try, I said, well, suppose we've got another nucleus around. Can we transfer the excitation to the other nucleus? So how do you transfer the excitation? You do it like this. You go, whoops. Yeah. No, I don't have that graphic. Okay, so you go from one to the other, and then this one comes down and down converts the radiation, and you end up with both guys in the ground state. So this is another mathematical model, but it has a big advantage that the Coulomb barrier that made this transition be very weak doesn't need to apply for this transition. And if you can transfer the energy from the one process to the other, then this one can down convert okay. And this is actually a much healthier and much stronger model. It solves these two problems, and now the matrix element's much larger, so at least we've got a fighting chance of doing something. Unfortunately, no long-lived states. Got all these other problems that we've got to deal with. Anyway, the current scheme, which it tries to address all this, the one I'm working on now, works this way. You start with a D2 in the excited state, and you've got these ground state nuclei with low-lying excited states. And the idea is to cache that one in for a lot of these little guys. So you do that. And now these little guys, if you can down convert the radiation from the little guys like that, then you can turn them into the energy into vibrations. And this is far more promising. And this is what I'm interested in. This is what I'm working on. So it solves this problem, this problem, this problem. The long-lived states are potentially available. Now we only need about 200,000 quanta. And in high harmonic generation, they do about 10,000 quanta. So out of the box, this is actually getting to be close to what it is you might imagine could work. But the spin boson model doesn't work. How do you couple the nuclear degrees of freedom vibrations still remains a problem here, so we still have more work to do. On this one, I worked for a lot of years. I actually found that you could solve it if you added loss to the spin boson model. You could get good down conversion. There's one reference here. There's a lot of references. I spent a lot of time working on these models, and I'm happy to talk to the interested physics types among you about this at length. I babble on for hours about it. Finally, how do we couple the nuclear degrees of freedom of vibrations? And that was the last problem to worry about. In 1989, they were arguing that trying to have the rest of the lattice interact with the innards of a nucleus is a little bit like having the moon try to impact what's going on inside of a glass of water. moon's a long ways away, and the forces are perturbative tidal at best. So this was pointed to as the reason why none of these coherent schemes would ever work. So it turns out, there's some fine print. There's some fine print here. Fine print goes like this, that nuclear forces depend on velocity, something a little bit like magnetic interactions. So you have magnetic interactions and you go in a moving frame, or you charge the moving faster, you get a bigger magnetic field and it changes the force. And in free space, everything's relativistically boosted and nothing happens. But if you move back and forth, go back and forth, you end up picking up a net interaction. And something can happen. And, well, it's actually pretty simple. If you start out with a relativistic many-body direct empirical model and you do a fold equal 2's on the center of mass, you can get the separation, and here it is. So internal nuclear degrees of freedom, center of mass momentum, the thing's moving. There's a coupling between the vibrations and what goes on inside. You'll be tested at this at the end of the hour. Okay, so this is the focus of my effort these days, and this scheme on the face of it looks like it deals with all the problems. So I'm really excited. I mean, we haven't had this for all that long. And I thought, great. So I go and I regale all my friends with it. And they look at me and they scratch my head and they say, well, you've been out in the sun too long. You know, you work in the cold fusion business, you get hammered, and over the years it takes its toll. And they say, there's help available for me. And so I think, well, what we need to do is we need to go in the lab and test. See what Mother Nature thinks about it. My friends to turn up their no, it's not like. So the issue is, if you do a Fleisch-Pons experiment and it works, you don't get to see how it works. You put in the deuterium, you get out the helium, people measure the helium coming out, but you don't get to see microscopically because you don't have commensurate nuclear radiation coming out. What we need is we need a different experiment where we can see what comes out. We need an experiment where we put in vibrations. If the nuclei get excited, then they radiate or they emit something and we measure it. We need that experiment. If we want to understand Fleisch-Pons mechanism, we need an experiment like that. So the idea, start with the nucleus, put in vibrations. If you can do this, which would be a really cool thing to see, and then it radiates, and if you have a detector and you can see what comes out, then you can say, I did this. I made this happen. So, first question, if you want to do this, what nuclear levels are there? Well, there's several nuclear levels down between 1.5 keV and 14 keV. This iron transition is the most studied transition in Mossbauer studies. There are 5 or 6 experiments out that potentially have an interpretation like this. There's the Gotzi experiment, which was a cold fusion experiment. But in this cold fusion experiment, there were some splotches on some X-ray film. And Gotzi, this drove Gotzi nuts, and he analyzed it. One interpretation for this would be upconversion of a silver nucleus to a state up at 88 keV with a gamma coming out. I actually think more likely in this case it would be the subdivision to come down to make this state. But the cool thing about this one, even if it's not as good of an example as I like, is that there's some potential effort put into the identification of which transition was involved. There are other experiments. Carbute glow discharge got collimated X-rays at 1.5 keV. And I thought, 1.5 keV, that's near where the mercury transition is. Maybe there's mercury being excited. And Kornilov and Vysotsky experiments at 1.5 keV and also from more keV. Emission from metals being excited. Again, one interpretation, not their interpretation, is that perhaps the vibrations are being upconverted and making this happen. So we want to see this in our lab. We tried and failed with exploratory experiments with a water jet and direct vibration experiments. They just didn't work for us. Recently, threw in the towel and tried a simpler experiment, which was going to be an excitation transfer experiment. So the idea is we have cobalt-57 here. Cobalt-57 decays and makes a state at 136 keV, which decays to a state at 14.4 keV. So what we wanted to see was to see whether we could take the 14 keV state and move it by excitation transfer. So we're going to use transducer and blocks and do all this complicated stuff. Our experiment failed for what we were looking for, but we saw an anomaly. Let me show you what we saw. So there's a little line here, the 10K alpha, which is photoionized by the decay of the 136 keV state. That decay is exponential with a time constant of 271 day half-life, which is a half-life of the cobalt. On the nuclear 14.4 keV transition, this is what should have happened. This is what did happen. On the K alpha, which is made in part from the decay of the cobalt, but also in part from the decay of non-radiative decay of the nuclear excited state, we see the same thing.
You're saying you're seeing non-exponential radiative.
We saw non-exponential decay, and the way to think about it is that before Florian turned down the bolts on the wood clamps, it was going down like this, and when he turned down the screws, the thought is it went up like this. And you could say, well, how do you know that? You couldn't see that because the detector everything wasn't in place when you did it. Which leads us to a different experiment. Before the different experiment. Tightening the clamps produce the non-exponential decay. The thought is that the relaxation of the stressed steel creep motion dislocations, which makes terahertz phonons. The model says, you want to make this kind of thing happen, make terahertz phonons. So the observations support the phonon nuclear coupling ideas. The effect, at the moment, an up conversion effect is on the table for this thing, that instead of changing the decay rate, we made new excited state 14.4 keV. That's what we're thinking. And again, this is a preliminary result. We need lots more work on it. We're going to try to work with other labs to get a confirmation. However, let me go back. It's a subsequent experiment done in August, where here Florian put in some heater pads, and we could turn the temperature up and down. And when we turn the temperature up, the K alpha goes up, then it takes its sweet time coming down. Each yellow, white is 1 day, another day, another day, another day. This is in slow motion. Another heater pulse, another response. Here, a longer heater pulse going up to higher temperature, bigger response. We turn the heater pulse off, it relaxes back down. So apparently, they've been working on these models forever. So the math has always been saying that this kind of thing you ought to look for, and maybe it could happen. My jaw is still on the ground from these experiments. Namely, it seems to happen again and again. In this particular case, the big thing I think might actually be indicating a down conversion initially, and when we apply the heater pulses, there's more phonons there. Maybe when we add the phonons, we're getting an up conversion effect to go on. So if that's actually real, then we have a chance to see the mechanism. Robert.
What is that actual experiment? I mean,
It's very similar to what was shown here. The only difference is there's heater pads. this isn't here, this is on the bottom, this is still here. We're looking at this one. So we got pressure, stress applied by wood blocks that have been tightened, and then heater pads on top. And the way heater pads also heat up the wood clamps down harder. I think that's the primary effect that we're seeing. We're actually dynamically changing the pressure. Of course, you say, why don't you just get a stupid actuator, computer control? Why you go out there? Anyway, we're going to try doing other experiments to do that kind of stuff. Yeah.
Which you're trying to observe
we were looking at this one. Plus, there's on the nuclear diagrams the K alpha is not usually shown, but there's a K alpha line as well. Anyway, these results are new.
What's the transducer?
The transducer here was put in to try to see if we could use 2 megahertz vibrations to make this magic happen. You know what Mother Nature thinks of our 2 megahertz vibrations? Not very much. But I think Mother Nature likes the terahertz vibrations lots more. Okay, back to Fleisch and Pons type experiments. So Dennis Letts and Dennis Cravens pioneered the one laser experiment. The basic idea, if you come in with one laser, you could stimulate an excess heat burst, and then when you turn your laser off, the heat burst would go away. I thought, that's fantastic. Why not try a 2 laser experiment? Because you could tune them and scan the laser frequency, and you could excite a different frequency in the terahertz region, and that's where the phonon modes are. So laser 1, laser 2, different frequencies, palladium cathode, platinum anode. Turn the lasers on with the right polarization, light frequency difference, initiate an excess heat burst. It goes on, it stays on. In some of his experiments, he would turn the lasers off, and it would still stay on, which was very radically different than the one laser experiment. The interpretation is that by establishing the vibration in the right frequency, we would draw down the nuclear energy and put them into the modes. And in this case, it would self-sustain the vibrations. That keeps on going. Dennis called, he says, how do I get it to turn off? I said, well, you can lower the temperature, you can dim down the current. Alternatively, do you have a firearm? I was not serious about the last. So he did experiments over 2 years scanning the difference frequency. There was a resonance around 8.3 terahertz, around 15.7 terahertz, 20.7 terahertz as I recall. At the gamma point here, the group velocity is 0. So if you put the energy in, it stays put. So this corresponds to this. And that one is another point where the group velocity is 0. And the energy stays where it's put. It's this one. So it's very good. Take my bow. What about this one? I didn't predict that one. And the thought is that if you add hydrogen impurity, because the system runs in an atmosphere and light hydrogen gets in the system, but the L point for the hydrogen impurity is right around 21 terahertz. So that's my best guess as to what that other peak is. Anyway, this experiment supports the notion of down conversion of the nuclear radiation. I was talking to my friend Mitchell Swartz, and he says, what kind of experiment we got to do that would, instead of support the idea of down conversion, would prove it outright? So what do you got to do? I know, do a Raman experiment. If you can do a Raman experiment and see the anti-Stokes line come up, that would tell you that the vibrations are very strong, and if they dominate everything, then that would do it. So my friend Mitchell, he builds a Raman spectrometer system, and in his nanner system, he runs, and when the thing's off, he puts in 532 laser. He sees the Stokes, and I'm going to guess this one's at 4 or 5 terahertz in a palladium system. He turns the current on, which gives him some excess heat. The Stokes is here. Now there's an anti-Stokes line stronger than the Stokes in his system. And basically that is measuring for the presence of terahertz vibrations. and he's got strong terahertz vibrations in the system when there's excess heat produced. And the peak is, so I recall, it's somewhere near 4.2 terahertz or so. And there's a zero group velocity band associated with the zirconium in the system that's near there. Ian, we talked before about how the excess heat goes up after a threshold with current density, thinking, why should that be? Well, if you've got electrochemical current coming in, you've got deuterium diffusing. Every time it goes over one of the barriers, well, when it lands, it rattles things, and rattling things is terahertz vibrations. So the interpretation is that this effect is due to terahertz vibrations. McCoubrey made a predictor. His predictor said, well, excess heat's linear above a certain current threshold, quadratic in loading above a certain loading threshold. And we show data for these plots. And after he and I were discussing these things, I twisted him to think about the flux as being connected to phonon generation. So he tried making an empirical model where this was added. He had an experiment which showed a breathing effect. So the deuterium would go in and out independent of his doing any current. And when he added the term to his predictor, he was able to go between the experimental data and his predictor, and the improvement improved dramatically. He was able to get heat bursts that were associated with the breathing mode to show up with this kind of predictor. So the breathing mode, deuterium going in and out, very noisy, making terahertz vibrations, connected with the excess heat production. Irv Dardick said, let's use superwaves. I said, what the heck is a superwave? He said, that's a superwave. I said, well, that looks just like a modulated thingamajiggy. Anyway, energetics use these things. They saw interesting results. They had a small number of experiments which gave a large excess power gain. And this is interesting by itself. Energetics tried to replicate it. They could get factors of 2 and 3 fairly regularly, but getting another factor of 20, only a very small number of times did they see that. They measured temperature in several places. The input current went up, input power went up a little bit. So in this experiment, again, input power less than a watt, thermal output power more than 20 watts. This is the kind of thing that would be interesting if you wanted to make a commercial product, which is what energetics was trying to do. They did not succeed. Here's the temperature data associated with it. I'm not going to spend more time on this. One of the things that the superwaves is good at, I was trying to explain to some of my friends. They said, well, why is this interesting? I said, well, what's a superwave? I'll tell you what a superwave is. You ever come into your office and open your desk drawer, but your desk drawer wouldn't open, it was stuck? What do? Well, you take the thing and you rattle it, and the faster you rattle, the harder you rattle, it gets it unstuck. That's what a superwave is. So in terms of getting your deuterium in the palladium, well, the deuterium trying to get in it gets stuck. So the superwaves apparently clean out the stuckness. Superwaves allowed at SRI to get to loading, in this case about 0.97 or so, which is not an easy thing to do. So it can help get the loading higher, and when you get excess heat, it moves the deuterium in and out, which makes terahertz phonons, which in my view is a good thing. We talked about helium. Daniel Gozzi at a university in Rome showed up one day and presented data where he saw excess heat bursts, so excess heat watts, and he had a helium detector that they'd spent years building, debugging, and they'd given several presentations on. What they saw is when there's excess power, they saw a time-resolved helium signal. More excess power, more helium. McCoubrey and I were sitting next to each other when we saw this, and we nearly fell off our chairs. This was shocking. There have been other experiments correlating excess heat and helium, but none time-resolved like this. When I give my IAP course, I go on much longer about this issue. But helium's time correlated with the excess power. People measure the total amount of energy and the total amount of helium-4. In a lot of experiments, you get less than you would expect if there was a 24 MeV mass difference from D2 to going to helium-4 reaction going on. We talked about this for years. At SRI, they did an experiment where they had a helium leak-tight system. They saw excess heat. They got the helium out, and then they made an effort to scrub the helium out afterwards. And at SRI, when they did it, they got the energy per helium atom measured to be 24 MeV to within 4%. One other experiment was done like this at NEF Frascati. They got within around 10%. Again, the accuracy wasn't too high for that measurement, but it was within experimental error. I'm of the opinion that bulk palladium deuteride, if you get all the way up to loading of 1.0, which you'd think ought to be the cat's meow for this based on what we talked about earlier, I think it's inactive, it's inert. Why would it be inert? Well, if you're trying to make helium-4, that means you want to get two deuterons together. But an octahedral site's here, one's here, one's here, one's here. These things are far apart. It's hard to get them together. And what prevents them from getting together in palladium deuteride is that the background electron density is too high. Support for this point of view is in many experiments done during the last decade with extremely high loading, with loading above 0.95. And these wonderful experiments that isolate palladium, deuterium, and loading. No flux, in fission ponds, the palladium was very dirty, lots of impurities and so forth. These experiments are usually done with a little bit purer, better palladium. But when you load very high and you don't do anything else, you get a system which, like I say, I think is inert. And there's experimentalists who've listened to Mike McCoubrey and said, well, I'm going to get the highest loading around and I'm going to see excess heat, and they get super high loading and they come away with nothing. So if bulk palladium deuteride is inert because the electron density is too high, what do we got to do to fix that? Okay, we got to get the electron density down, the background electron density down. How do we do that? We take one of the palladium atoms, we pull it out. Much less electron density to the palladium, much less background electron density that way. So that focuses the attention on vacancies. And as it turns out, when you add hydrogen or deuterium to palladium, if you start out with pure palladium with no hydrogen or deuterium, it takes about 1.6 electron volts to pull a palladium nucleus out, or palladium atom out. But if you start adding hydrogen or deuterium, it takes less energy to pull it out, until when you get to loading near unity, it turns out that a vacancy phase structure where the palladium has been pulled out and is elsewhere in the lattice is the thermodynamically preferred system. I understood this from the literature in the early 90s. I said, we've got to do something about this. And it turns out some of the Japanese understood it, and they had experience and labs. And Fukai produced this structure, reported it in 1994. And the way he did is he used a diamond anvil cell, put in the hydrogen, loaded into the palladium, and then heated it up. You need to heat it up to get the vacancies to move, or the palladium to move, leaving vacancies. So this material's been made, it's been studied. And I think it's really interesting because it forms at very, very high loading. So in the 90s, I made up an estimate based on values for the thermodynamic parameters at the time. But basically, for palladium hydride, if you get a loading of about 0.95 at 300 degrees, under those conditions, the Fukai structure should be thermodynamically preferred. Now, unfortunately, if you make your cathode reach high loading and you want to see that structure, usually people aren't patient enough to wait to see it. You'd have to wait something in the neighborhood of 1 to 10 million years. And people these days, they're not patient. Which is why Fukai went to high temperature to speed up the diffusion to make it go faster. So if you can't make it in your cathode, what can you do? Well, the idea is that if there's new palladium deposit on the surface, so for example, I think in the original Fleisch and Pons experiment, some palladium would dissolve off of the surface, go in the electrolyte, and then recombine. And evidence for that is when they did surface analysis, they saw platinum. Platinum comes from the anode. And you can say, well, in a base, there's no way to get the ions to do it. I think, well, there's these complex... Anyway, that's a whole nother story. But in 1991, Schbach reported excess power in a co-deposition experiment where instead of having to wait a month or two like Fleisch and Pons and SRI and everybody else, you had to wait 20 minutes. And this is supportive of the notion that high loading, you co-deposit, you make vacancies, now you got a place to make things work. In Pam Boss's experiments, she does co-deposition at low current density and she sees energetic particles. I think when you don't get excess heat and the gain's not high enough and things aren't perfect, it's like an engine sputtering. In this case, the sputtering pisses out neutrons and protons and tritons and helium-3 at low amounts, also energetic neutrons and other stuff. Letts came up with a protocol where he co-deposited palladium at high current density, which means very high loading, which means you ought to make the vacancies. But if you do that at high palladium concentration in your electrolyte, you get this crud on the surface which just falls off and it's no good for anybody. And Lett says, I know, reduce the palladium in the electrolyte, which slows down the deposition rate, and he got stable palladium co-deposit regions that way. And this is what he saw. That co-depositing the palladium excess heat replaced the D2O with H2O, and in this experiment the excess heat goes away. And people said, well, it's just recombination, but if it's recombination for the deuterium and not for the hydrogen, how does that work? Anyway, Letts has seen this also with other systems, nickel co-deposition, gold co-deposition, other things that are similar. What about nano-palladium, also nano-nickel? Nickel's a lot like palladium in terms of the vacancy part. The solubility of deuterium and nickel is much lower, so it's a different problem. Nanoscale, the surface energy is a much bigger effect. If you're going to make vacancies at high loading, you'd expect them to form much more readily in the nanomaterial. Around a vacancy, the O sites and T sites are near the same energy, so the full occupation in the Fukai phase gives a loading over 3. The Japanese recently reported loadings over 3 in their nano palladium. Consistent with, but does not prove vacancy phase occupation. We really need some experiments to clarify what in the world's going on. And there's been observed excess power release in the gas nano experiments, which is, again, encouraging. I'm a fan of no. I gave a talk once before where I was trying to talk about the nanner, and the nanner figure didn't display, and I've got the same thing happening here. All right, let me try to describe it. In Mitchell's nanner, he's got nano palladium or nano nickel, nano palladium nickel in a zirconium oxide matrix. He processes it, he treats it, he can load it with deuterium, he seals it up, and then now it's loaded. So the loading is disconnected from, he's got a sample where the loading is disconnected from the operation. It's a loaded sample. And he runs electrical current through it. And when the electrical current goes through, it produces excess heat, and it does it reproducibly. So this is from one of his publications, but here he runs power through a resistor, and he measures the power output. So the blue is the in and the red is the out. Then he puts power in the nanner, a similar amount, and the thermal power coming out is huge. And then he goes back and puts it in his resistor, and he gets power balance for his calorimeter, and he puts it into his nanner and gets big gain. So he did a test like this at MIT during one of the IAP courses and saw a power gain of 14. I think this is a little bit more than 14. It's dynamic in this case because he'd exposed it to a very strong dynamic magnetic field earlier, which seems to have a really big impact on the nanners. Anyway, so this is basically, it makes use of the nano material, which I think makes some vacancies. He can get very high loading in it, and he can do the excitation with electrical current, and electrical current makes terahertz vibrations, which is a good thing. Okay. Excess heat with hydrogen. So what about hydrogen? Palladium hydride experiments were used as a control in the early years. On the other hand, Fleischmann told people informally that he had seen excess heat bursts in hydrogen-loaded systems. Mills and Knisses claimed excess heat in nickel hydrogen or light water nickel electrochemical experiments. Piantelli studied gas phase nickel hydrogen experiments. I'm interested both in experiments, but how this kind of thing might work. The idea is that light hydrogen contains some amount of deuterium. HD can make helium-3, and it's the kid sister to the D2 to helium-4 reaction. So I tend to look at the hydride, the light water systems, as if they work, and I think Piantelli's surely worked, and the Japanese have gotten some positive results. I think it's due to this one. How can you tell? Well, if you could measure helium-3, that would settle it. So far, there's not been a test yet where you've got good excess heat in a light water system hooked up to a good mass spec to test, like was done in the helium-4 case. On the other hand, Mitchell-Schwartz added some deuterium upon my twisting his arm to do it to a light water system. And he found that with some modest deuterium increase, the power went up, the excess power went up at different operating points running, which again doesn't prove that the light water system is an HD reaction, but it's at least consistent. In Piantelli's experiment, he's got a nickel sample in a chamber. He puts in hydrogen gas. He's got a heater. He's got pumps. He loads, then he deloads. He loads, he deloads like a dozen times or so. Each time more hydrogen goes in. The solubility is very poor. But on the other hand, if you make defects, for example, you make vacancies, you can increase the loading each time. And then when you're ready to go, the system's all ready. What he does is he'll dump out some, or he'll lower the temperature and raise the temperature. And in a sense, what that does is it brings in the hydrogen and pushes it out, so it gets diffusion, which makes terahertz phonons. And in this case, after he does it, in the after state, he gets a temperature increase. So he's getting about a 20% excess heat gain in this case. And he also gets an inversion of the temperature, so the outside is now colder than the inside. So the nickel is the source of the heat. He sees an awful lot of other effects. In that case, he's got a cloud chamber, and when he pulls his nickel out and puts it in the cloud chamber, he gets all these tracks. He gets alpha particle and proton tracks in the cloud chamber. Nickel, you have to go up to 400 megapascal near room temperature to get across the miscibility gap. And he certainly doesn't have that kind of pressure. On the other hand, he's got impurities in his nickel, and in the miscibility gap, he's got areas where you have very high loading. You don't have the mixed loading. You have some of this and some of this, and some of this looks to be high enough to get the vacancies. In the nano experiments of the Japanese, here's an example of a hydrogen run in a nickel with some copper in a silicon dioxide matrix, and he's getting good excess power, 10 watts excess power. What's probably more interesting is he's got data points here for the energy produced. Energy, yeah, he's got quite a bit of energy, 100,000, 10,000, 100,000 times, or electron volts either per H or per nickel atom, depending on how you measure it. So the energy produced in these experiments or measured in these experiments is much greater than chemical. What about the future? So at a high level, can we move in the direction of commercial product? There are commercial efforts working on that now. I'm actually interested in the larger scale organization. The number of folks who've worked on cold fusion over the years, in 1994 there were about 1,000 people worldwide working on cold fusion. Today the folks that have been through with the whole field the entire time, we're probably down under 10, and each year labs are closing, Coalescence is closing, the MISU effort is likely to, scheduled to shut down pretty soon. People are retiring, and if you want to move forward to a commercial product, you're going to need folks that know something about it that are still standing, and you really need public support for basic research. How do you get a venture capitalist to laugh? You encourage them to support basic research. Anyway, let me talk a little bit more. If you're going to have a new technology, you need a basic research foundation, you need engineering foundation, you need work on application, you need prototypes, and maybe products goes on top. Okay, how do you do that? So this is I'm more of a scientist than a business guy, but I figured Silicon Valley, we've got to have a business model. So here's my view of what the business model is for normal scientific research. You get public support for the basic research, for the basic engineering foundation, and for applications you get government support. There's also, at MIT, there's a lot of industry support, so this is public and industry support. And when things happen right, researchers, they get publications, they like to write papers, they get career advancement for their publications, and good things happen. To get prototypes, you've got to get research, or you've got to get resources from somewhere else. And if you watch Shark Tank enough, you figure out that the investors come in after the products are developed and they start selling and they start making a profit, and then the investor. Anyway, again, I'm not a business wonk, and it's possible that my version of this diagram might be biased a little bit from the last 28 and a half years. What happens in the cold fusion business? So the cold fusion business, government support, public support, basically is not there. It's not there today. There was a little bit in previous years. You can say associated with the Japanese program, there's quite a bit of public support for a while, but today, no. So then you have researcher supporting the basic research, the engineering foundation, the applications. And in recent times, you have angel investment coming in, trying to make prototypes and putting money for applications. And so Dewey, this is IH has been supporting some of our basic research, so there has been some support from investors in this direction.
For basic research, you just use Kickstarter, right?
We can talk about that later. Okay, so there are some publications and presentations coming out of this model. For the angel investment into application prototypes, what we're learning is that when investors put in money to get things done, they do it to get commercial advantage. And you don't get commercial advantage by publishing. And so the field has been changed dramatically, that there's not very many researchers supported this way that are publishing papers anymore. So that anyway, it's changed the field dramatically. I went and I talked to one of my friends at a funding agency, and he said, "Good news. we can support your research. That's great. The bad news, you got to do some things first. First, you have to solve the research problems in your field. You got to publish the result, you got to present, you got to bring the scientific community on board. Oh, and by the way, these little things that you have to do before you can get funding, do it on your own nickel, and then come back and knock on our door. If you want a technology to come out of it, this is not the way to do it. To make technical progress, you got to do the basic research. I'm sorry for being so radical here and revolutionary. You got to do the basic research. You got to do the engineering, do the basic engineering. Got to do the applications. You need people to work on it. You got to make a way to get your people not get their careers destroyed working on it. You need places to do the work. You got to have resources, and there has to be a way for the researchers to actually benefit from doing the work. And in this field, that's not an easy thing to do. And then you get the new technology. So for my nickel, the cold fusion, is it real? Is it ready? Okay, it's not ready. If you want it ready, you got to think of this field as like any other field. You want a technology, you got to get the foundation laid. You need support to build the foundation. You got to get the basic research done. You got to get the engineering research. And it can be done, but you don't do it by destroying careers of people in the field for 3 decades. Some specific approaches, I have been a big fan and continue to be a big fan of Mitchell Swartz's nanner. I think technically it's an elegant way. It addresses the big issues if the system works the way I think it does. I like the Japanese nano work. I like what they were. I was worried initially, but I like how that's been turning out. I like their organization. They found a way to get support from their government, from industry. I like the Piantelli nickel hydrogen experiment in principle. I like because nickel and hydrogen are cheaper than palladium and deuterium. Mizuno has an experiment with tungsten light water that basically took off and exploded. I don't like the explosion part, but if it worked well enough to do something like that, then it's a system that really needs more experimental work. I like what Robert Godis has been doing. I like that he's been bringing people to test his system, and I like that he's going more public and letting us know what's going on. Bravo for you. Bravo. I like the Let's co-deposition experiment. I like the vacancy phase approach. I think super waves remain interesting, and there are a lot of other things I would like. I would add to the list. And this is Martin Fleisch and me rubbing noses years ago during half-year times. Anyway, thank you for your attention for the second time. Questions or comments or thoughts? Way back there.
What's a photon?
Good question. If you have a vibration, vibrations, if you think about them quantum mechanically, take the total amount of energy that's there classically, divided by h bar times the frequency, and you get the number of phonons. So phonons is one quantum unit of vibration. Other question?
What is the significance in your mind of vacancies?
So if we didn't need vacancies, if we could get it to work in bulk palladium deuteride, things would work much more easily technically. But doesn't seem to be observed to work in the lab. So in my view, you're looking for a place where you've got a lower electron density. So if you take a palladium atom out, where it's not, the electron density, background electron density is lower. So that gives you a place where you can bring have the deuterons get closer together, sort of close to where the palladium atoms are. So where in the bulk, the high electron density means that if you... Can you hear me with this?
Yes.
Yeah, the high electron density means that states that are that push the atoms apart get occupied. Electron orbitals that are anti-bonding get occupied. So if you can lower the electron density, you can avoid occupation of anti-bonding states. And that's why, in my view, the vacancies are critical. I think that's where the active sites are, where the vacancies are. So, no.
Rossi doing anything useful?
Okay. In the beginning, when you were showing the negative results and the different filters on them, maybe you said this, but I missed it. Did you do the same filtering on the 39 positive experiments, and what what were the results of that?
I didn't do that on the equivalent 45 positives.
Wouldn't that be interesting?
I'm sorry, what?
Wouldn't that be interesting?
It would be interesting. Part of what I was thinking is that I had interacted with most of the groups that reported the positives, and essentially all of the groups that had been reporting positives went to the meetings. They knew about the correlation between loading and excess heat. Basically, every group that could field a measurement of the loading did. And so if I go back to do the same filter as you suggest, I think most of them would survive and would mention loading and would try to do a measurement of it.
So Pons and Fleischmann originally did discuss loading and all that?
So Pons and Fleischmann argued that you needed high loading. Their argument had some positive features and some negative features. The positive feature is that they discuss loading not in terms of resistance ratio measurement, but in terms of a reference palladium electrode that they would put into their system. And they'd measure the voltage difference between their active cathode and the reference palladium electrode. In an ideal world, the voltage increases when the palladium cathode is loading. So this theoretically gives you a way to measure the loading. The headache is there's two headaches. One, you've got to calibrate it, and two, there's an offset. And so Fleischmann misinterpreted the offset and the associated fugacity and got himself into a heap of trouble with the physicists by doing so. But Fleischmann, in his reasonably obscure way, was doing his best to explain that the system needed a high loading. And if you go and you look in his very first publication, you can find a discussion of that as being an issue, although it was very much not appreciated by the people in the field at the time. I missed it completely at the time.
Does the establishment science now believe that you can create excess energy?
No.
So they don't believe the experiments that you've shown us?
If I'm not mistaken, I think I had a friend in the physics department I had one friend in the physics department at MIT years and years ago, Hermann Feschbach, who I respected greatly, and I mourn his passing. I think it was ABC News wanted a comment from somebody at MIT on a cold fusion years and years and years ago, and they requested that I comment. I went through the MIT News office, and the MIT News office said, why don't you talk to Hermann Feschbach? And Feschbach said very simply, I don't have to look at the experiments. I don't have to look at the data. I know it's wrong. The effect itself is so radically at odds with what we know in nuclear physics from incoherent reactions that even a contemplation of it is not something you do without very, very, very good reason.
Hey, Charles, why don't you give your story from today?
Well, I was just going to say that the analogy.
Loud. So
Well,
everyone
the
can hear.
analogy that most people I talk to would say, the analogy that most people I talk to in physics would say, it's like believing in like being a biologist but not believing in evolution. So it just no one's going to talk to you. There's no. You can't write a paper which has just a mathematical paper and they just won't read them. So it's. Although my advisor did suggest what you suggested on the non-radiative decay process. When I spoke, but he's not a physicist. He's not a nuclear physicist. So he's just, we specialize in non-radiative decay in molecules. So the phenomenons those phenomena are very well understood.
Right.
Thank you. As I understand it, you believe that the primary reaction is deuterium forming helium-4, which by ordinary nuclear physics is a very low probability event.
About 5 times 10 to the minus 8.
Right. Why, if you're trying to convince the public or physicists at large, why not concentrate on experiments which produce helium-4, since there is no known way to produce helium-4 from electrochemical reactions, regardless of the apparatus, regardless of the interpretation. If you produce helium-4, something funny's going on.
Your point's well taken. I will note that experiments where helium-4 has been measured have been done, have been published, multiple publications of it. Such publications have not made any difference at all. And I think more generally and globally, there are a large number of experiments out there that have been done, which I think are fundamental, extremely important experiments. None of them had made any difference at all. It's just the way it is.
Both? Okay. Yes, to this point, what you need is a clear demonstration of the fundamental physics. And from your description, one of the interesting thoughts that occurs to me is you have this coherent system. It's going to pump out a bazillion photons, and the energy, or phonons, and the energy for this is going to come from a couple of nuclei. Is it possible to do the quantum mechanical calculations? They should be able to show this. If you had the right Hamiltonian, that this transition could occur. And I'm just wondering if you could attack it, shall we say, from a theoretical point of view to get a little more credibility.
So I am more a theorist than an experimentalist, and I put together said Hamiltonians, I analyze them, I get answers out of them, I write papers, I submit them to all kinds of journals, most recently to focusing on our journals for quite a few reasons. So far, there has been no interest. Previously, when I tried sending earlier versions of these kinds of computations in the mainstream journals, I got back reviewers' responses that suggested I'd be much better spending my time doing anything else. So I have not put in as much energy as I might have otherwise, simply because this is, to me, more a social problem than a scientific problem at this point. I have the tools to deal with scientific problems. I don't have the training and the tools, the ability to handle the social problems. I wish I did.
There are quite a few other theories out there. The Whittam-Larson theory and Mills hydrino and some other theories having to do with or related to cold fusion. I was wondering if you think any of those are serious theories in the sense that yours is.
I will point out that the Whittam-Larson theory managed to be the most successful theory for cold fusion I think that there has ever been. I have had all kinds of people come up to me and say that they are certain that it's correct and that it explains what's going on. So Whittam and Larson and their colleagues are much better at interfacing with the community than I will ever be. I do not think their theory is correct. I've written some papers trying to explain how it works and how to interpret it and what the headaches are and what the issues are. I haven't seen that it's had any effect. I've had Randall Mills come to my office twice, and I've spent time trying to talk to him to explain why his models are broken, and it's not done any good. I don't know what to do. Mark Davison's got some models that are very interesting models. They're very serious, and he's put a lot of work into them, and he's gotten them published in mainstream journals. Congratulations, hats off to you, Mark.
Yeah, so can we go back to the...
Oh, I'm sorry.
Excuse me, can we go back to the D to HE4 question that somebody asked before? Why, if that works and that's reproducible and that's the best candidate, what's holding that back from being commercialized?
I'm sorry, the nanner?
No. The question earlier where somebody said the best theory was D converting to helium-4. Why hasn't that, if that's good and it's clearly reproducible, so that's a question, is it good and clearly reproducible? Okay, so and if it is, what's holding that back from being commercialized?
Okay, if we're talking about a theory, I salivate at the possibility of my theory being able to be commercialized and that I could get the big bucks from it. Typically, it's experiments leading to applications, leading prototypes, applications, commercial product. So basically, if you have a theory, it can guide you as to what's going on and maybe give you some advantage to design something that maybe has a chance of working. But at the end of the day, you need something working in hardware to lead to a product, to lead to commercialization. My understanding of the various experiments that are closest to having a potential be commercialized work this way. The deuterium experiments, I think, are making helium-4. Go ahead.
So how many of those are there that work?
Many that work. Well, again,
is it 3? Is it 5? Is it 10?
No. When you say work is sort of a thumbs up, thumbs down kind of thing. To be commercially interesting, you need them to work well enough to do something good for somebody. So, for example, the power gain in the nanner is sufficiently high that, in my view, that if you could mass produce them, you would have a product which would be useful to people and that people could buy and get utility out of. I'm of the opinion that the SRI experiments worked. I think Fleisch and Pons experiments worked. I think the Japanese nano experiments are working. I think Lutz's co-deposition thing's working. I think Piantelli nickel hydrogen thing's working. You have a lot of experiments which are working. The minor headache is that right now, if you tried to mass produce the SRI experiment, the unit price would be quite expensive. Wouldn't do a whole lot for you. Wouldn't make much of a profit. So when you say commercialization, you're asking a little bit more out of an experiment than whether it just works or not, sadly.
Thank you.
Let's just say in a normal course of events, I come to your office tomorrow and say, I'm thrilled by your talk and I'm excited about the potential. Will $4 billion be enough? And if we did that and you had the good sense to accept, what would you do?
I would at first thank you for your kind thoughts. I know what I would do with 10 more K in the lab, and I have another student who's interested in working with me that I'm trying to arrange support for, so I could see my way all the way up to on the order of 100K that I would know what to do with at MIT. I've had discussions with colleagues about the possibility of much grander scale fantasies that go up all the way to $1 million. However, right now, although I'd love to have $1 billion to work with, it takes time to organize an effort that's going to be useful and meaningful. If there were support and the support were available for enough time to do some good with, then between folks I know and folks that are interested, we could put together basically an effort that would be aimed at establishing a basic research and engineering research foundation for the field, which is one of my goals, which is what I'm interested in doing and working in. So what I would do with such resources is basically push it in that direction to try over an extended period of time to bring people on board, get them trained, get the experiments, so the important experiments to get done, get the answers, get them published, and get some science to emerge out of the sacrifices that so many have made over so many decades here.
So maybe I missed it, but you, I guess, can your theory explain this dichotomy between the palladium-deuterium system and the nickel-hydrogen system? Because you showed this band structure for palladium and you matched it with these peaks, but why would that be different in the nickel system?
What a great question. In some sense, there's a lot of similarities between the nickel system and the palladium system, and there's some differences. The big difference is that in palladium, the background electron density is lower, which means the hydrogen deuterium solubility is much greater. In nickel, the background electron density is very high, which means that it's really hard to get hydrogen deuterium into the nickel, into bulk nickel. On the other hand, if you make vacancies, turns out, as near as I can tell from the DFT calculations, nickel Ranamana vacancy is the closest system to palladium that there is for a monatomic system. Mitchell-Swartz has seen reasonable operation of his nanners based on palladium or nano nickel in a zirconium oxide loaded with deuterium. They seem to work just fine. So it's not the case that nickel and palladium you can trade them off one against the other, but the guts of how they work, the underlying features of them that are important, are sufficiently close that I view nickel as a very attractive substitute for palladium in all of this, as long as you're willing to go into make Fukai phase type structures or high vacancy structures. Then in my view, you're basically talking about a very similar system.
Peter, we'd like to take just one more question and then remind the group that after the formal ending of the presentations, there'll be time up here. You can talk to Peter one-on-one with more specific questions. So just one more question.
Peter, why don't you set up a cold fusion center at MIT, like other departments have, and promote that fact to people like us that are alumni? And many of us donate money to the Institute, and I personally would much more interested in designating my donation for your fusion cold center than to go to some arbitrary fancy new building that the Institute really doesn't need.
I very much appreciate your kind thoughts and sentiments in this. At the present time, I'm doing really well to manage to maintain a low level under the radar effort in borrowed lab space, and to keep two faithful students supported, and have my credit card be able to buy the occasional gear when needed. There is no possibility at present of having there be any sanctioned center that has anything to do with cold fusion or LNR or whatever at MIT at this time. It would be, I don't know, it'd be easier to do like almost anything else than that. I have been known to remark that at MIT, cold fusion effects would not be accepted even if power were supplied to MIT to keep it running by a cold fusion power source.
Thank you, Mitch, very much, Professor Hagelstein.